Yep.
And
Um,
I see you have a lot of slides, so you're going to have to go very fast.
yeah, I'll fly through them. I'll fly through them. Don't worry. Okay, so the slides hopefully are visible right now.
Yes, go ahead.
Okay, brilliant. Okay, I'll just get right into it. So the idea is that we would like to improve primary vertex selection in events in the context of the Atlas experiment, and we're saying that basically by doing that we might be able to really recover events in sensitive topologies, like say for instance the VBF is invisible. So with slide 2, basically the way we choose a primary vertex right now, in a given bunch crossing, the idea is that you look for the vertex that has a lot of tracks attached to it. So you maximize the sum over the transverse momentum of the tracks that are attached to the vertex, and you pick the vertex with the largest sum PT squared. The idea being that that will always bring hard scatter interaction. But where it starts to fail is where you have topologies with very low visible PT to begin with. So something like VBF fixed invisible. I put a couple of example topologies at the top right of the slide here. And the challenge that comes with topologies like VBF fixed invisibles is that it's not only that you have low visible PT, but in the specific case, the VBF jets might end up being forward, and so your charged particles might land outside your tracking acceptance, in which case you don't have any tracks. So how do you pick a vertex? And then finally, as is any problem in bunch crossings, you might end up having, the other non-interesting interactions, the pileup interactions, landing too close to other pileup interactions, in which case they're reconstructed as one sort of jumbo pileup interaction with a lot of tracks attached to them. And then they will end up getting picked because they'll have an abnormally large sum PT squared. And sort of these things, these factors collectively sabotage the interesting, vertex.
Yeah, you need to move on. You just spent half your time on one slide.
Yep. Okay. So on slide 3, the idea is that instead of maximizing sum PT squared, you maximize this modified sum PT squared, where slide 4, you introduce a vertex grooming part where you basically drop all the tracks that are not along hard jets, and you also introduce a weighting factor that adds a large weight to tracks that are going into hard jets. Okay, how does this manifest? Well, the vertex grooming part will veto pileup tracks that are uncorrelated to pileup jets, to hard scatter jets, and then the track weighting part will boost the sum PT squared for vertices with very low visible PT. Okay, so in slide 6, in practice, what does it look like? So you're comparing the vertex selection efficiency with the pileup density, and the current method in black is compared with this new method in blue. 2 key points here. So you're seeing that there's an average improvement from 80 to 88%. But you also see that there's a correction in the slope. So you see that there's this downward slope on the black line, which is being corrected by the blue line. What does the downward slope on the black line mean? That is a function of your performance degrading as you have more and more pileup merging. Right? And the fact that that slope is being corrected in the blue line means that indeed that vertex, the vertex grooming term, is effectively vetoing pileup tracks. So that's very good, and that's what we expect this method to do. That's a great improvement. Okay. But that still leaves us with some questions. So as a cartoon, you can see here that there's 2 parts. The vertex grooming corrects your slope, and the track weighting gives you an offset improvement. But that still leaves us with a 10% inefficiency that we see in these plots. And where is that 10% inefficiency coming from? Well, that's because of tracks lying outside the tracking acceptance, right? So there's these 3 typical events that I've shown on the right here. That could be where you lose information. So these blue circles are your hard scatter jets, for instance. So they could lie completely outside your tracking acceptance. That's a cartoon on the top, or they're partially contained in your tracking acceptance. So these are the 2 cartoons below the top plot. Now, in the case where they're completely outside your tracking acceptance, you can't tackle that in the current geometry, at least in the Atlas experiment. That's something that we can address at the high luminosity ellipse, where the tracking acceptance goes all the way out to 8 to 4. But with the cases of the 2 jets being partially contained, with this whole track weighting term, we hope that we can actually recover these events and find the right vertex in these cases where the conventional method is expected to do fairly poorly. Okay, so the way we want to sort of sidestep and address this issue is by making an event category, at least in this, the current geometry where we have a finite tracker. The idea is that you classify any event that has 2 or more jets that are basically trackless, so they have very low RPT, and I've defined RPT on the slide for future reference here, as low confidence events, right? And anything that is not is a high confidence event, which means that there are tracks in forward jets in these high confidence events. And so you expect vertex selection to do really well there. But does it? So slide 11, we see that. So this is again vertex selection efficiency versus pileup density, but now I'm comparing the new method on all events in blue versus the new method on only the high confidence events. And we see that there is an improvement. So I'll just go with the main points of slide 12 here. Not only is the improvement, so you basically are all the way up to 98%, which means that the problem of vertex selection, at least as it applies to these high confidence events, is completely solved. And this is what we expect because there's no missing information anymore. All the tracks are in the jets, right? So effectively, by giving this track weighting factor, even the events where you had some partial information loss, you've actually completely recovered that, and you've maximized your selection efficiency. The remaining 2% inefficiency that you see on the spot is coming from topology, because so some PTW, just like some PT squared, is a topology unaware way of selecting your primary vertex. It doesn't really discriminate one topology from another. So if you have a hard QCD pileup interaction in your event, that will pretty much always trump your visible vertex. That will always be the one. That's why there's that little remaining efficiency. But it's good to see that subject to that, it's actually as high as the efficiency as high as it can be. What's also important is to realize that the low confidence events that were sort of vetoed from this plot, they can still be retained for physics. It's just that they don't have any vertex in them that we can reliably point to and say that that's the primary vertex. Which is kind of crucial because we're not throwing those events out, we're just saving them essentially vertexless. Okay. So on slide 13, we can compare the current method, sum PT squared, versus the new method, sum PTW, now on these high confidence events. And it's reassuring to see that the two main points of improvement that we saw before are still true here, which is that you get a complete removal of the effect of pileup merging by moving to this modified sum PT squared. And you get this really nice offset improvement to now where you sit at 98%, effectively having solved the problem of primary vertex selection. I think I may still have a couple of minutes left. So to wrap it up, really, the only thing left to see is what this would look like at the high luminosity LHC, where now your tracking acceptance is all the way out to 8 to 4. This is great. But of course, there's also much more pileup here. It's possible mu 200. So first point to note is, so we're again comparing the current method in black and the new method in blue. But you will notice right off the bat that these lines sit way higher than they did on the run 3 plots. And that's simply because the tracking acceptance is larger. So the efficiency is larger because there's no missing information. But also interestingly, the black curve no longer has that very, very clearly downward slope. And that's because the tracking resolution is much better at the high luminosity LHC. But you see that the improvement still remains. There's still an order 8% improvement here. And that's really coming from the track weighting term that boosts your, basically boosts these topologies with no visible PT. That jet PT term really ups that, the sum PT squared factor. And so, it brings you to 97% from your 88% that you would have had with the conventional selection mechanism. And once again, the only remaining inefficiency is coming from hard QCD, which we do expect to happen slightly more often at V200, simply because there's much more pileup interactions happening at V200. That's why it's maybe a bit on the order of 3 to 4% than the order 2% that it was at the, under the current conditions. And actually, that's the end of my talk as well. So the conclusion is we're proposing this new selection mechanism that exploits the correlation between hard scattered tracks and hard scattered jets. And in doing so, boosts the visible PT of low PT interactions like VBF fixed invisibles by completely removing the impact of uncorrelated pileup interactions and their tracks. And we also, for the current geometry, defined this new event category. And by doing so, crucially, save the events where there isn't a vertex from being thrown away due to an incorrectly chosen vertex. And so in essence, rescuing those vertices from those events from just being completely discarded. And I've just tabulated the improvement in the efficiencies down here, where we go have about 8 to 9% improvement across the board. But yeah, that was a very quick run through. I hope I didn't go over my time. That's all I had.
Thank you. Yeah, thank you very much. We have time for a question. I don't see any raised hands. People can still raise their hands, I assume. Okay, so I don't think we have any questions. So thanks again.